Okay, hi everyone. Welcome back to the second session of today. Our first speaker is Nicolas Tapia from TU Berlin and Weierstrass Institute in Berlin. He will talk about robustness of residual networks via rough path techniques.
Thanks, Michele, for the introduction, and thanks everyone for being here for my talk. So I'll begin with a little bit of an introduction to see what we want to do. And so the setting is that we have a residual network. These were introduced in 2016. And what they allow essentially is that they're built in such a way that you can train very, very deep networks in a stable way. And essentially what you do is that you take a usual network, which is here on the right. So it's the first one on the right. And you insert these skip connections between every couple of layers. This you can choose however you want to do it. And the morale of this story is that kind of instead of training or looking for response function f, you look for a perturbation of the identity, and this makes some of the properties, gives you some more stability properties. Right. So in essence, this picture here is what you do when you insert one skip connection. So you copy just the value that you have of your features at one layer, and you just copy it after a few layers, and you add it to the current features, right? So if you only look at what happens between skip connections, then what you're basically looking at, it's a system like this. So in this picture here, this point yi would be this. You just carry it to yi plus 1, which is here. And then you add some nonlinear function, which depends on the weights and on the previous value, which would be this part here. And if you look closely at this form, it really looks like some sort of discretization of an ODE, and this is exactly the point of view that Haber and Ruth Otto took in a couple of papers. And so they interpret this update as being some sort of approximation of this continuous time system, right? So T here would correspond to the depth in the network, which you can think of it as some sort of fake time if you want. And you're trying to approximate the behavior of a control system like this. So the weights in the network would be your control, and the response of the control system would be the evolution of your features. And then the trailing problem is posed as an optimal control problem. So here L is the loss function, which depends on the output layer and the weights and the biases. And so the update between the layers is, again, as we said, some sort of Euler scheme for this ODE here. So this H parameter here is just to make it so you can play around with the scales. But so it's fixed beforehand. And it relates to the depth of the network. What they also need to do is that they insert this regularization part here, which is the R function. So you modify your loss function, and you add a penalization for the variation of the weights. Because as you see here, you're sort of looking at a controlled ODE. So if the weights are very rough, or vary a lot between the layers, then the behavior of this system probably won't be close to the continuous time one. So what you need to do is actually penalize the huge variations in the weights. Right. And so this alpha here is an hyperparameter that you have to tune. So our point of view is actually to try to do away with this regularization and say, okay, if you have some update that looks like this, probably it won't be close to this system here, the continuous system up there, but it would be close probably to a rough ODE, to the solution of an RDE. And this you know how to control. And this even makes more sense because in practice, you initialize the weights matrix by random values. So at the beginning, you start with something that looks like a Brownian motion, or could even be worse, right? So you put random values in your initial matrix, and then you evolve the system using this, right? So Okay, so we will see some plots afterwards. Right, so this is, here I've taken an actual trained network by the same guys that introduced this. So it's one set of weights that come from the network that I showed you in the picture at the beginning on the right. And this is a 5x5 submatrix. And you see that, okay, it doesn't look very smooth, but also it's hard to see if it's rough or not. And so if you plot one of the components, it actually looks like this. So, right, so the penalization scheme would actually give a high value of the penalization for this, and you probably try to steer away from this kind of behavior of your weights, right? But this is an actual weight trajectory that you would get after once full training, right? So this is, each point here in the plot corresponds to the weight for one of the features along the layers. I only looked at the skip connections. Why? Because in the architecture, they sometimes introduce some batch normalization, which means that you must multiply everything by a diagonal matrix. So this kind of introduced an artificial roughness, because between these layers, you're jumping from 0 to any other value, right, off diagonal. So here I only looked at the skip connections. Okay, so we propose to put it in a slightly different form, which you can do by actually adding an extra layer before the input layer. So after the input layer, you apply the nonlinearity once, and then you keep your current architecture. So it looks like this. So the update at the skip connection now looks like this. And you absorb all these batch normalizations, etc., that you do in the F. And we study the behavior of this propagation here directly at the discrete level. So we don't assume that this is approximating some sort of continuous system, which of course you can analyze after the fact if you know that your network is very deep, which would correspond to a small time step for the numerical scheme. And so the goal of this project is to obtain a bound on the difference in the output layers of your features, given that you know the distance in the input layer. So this is some sort of stability result that would tell you how far or how different can the response of your network be if you give it two different inputs after you have trained. So if you know the trained weights, you want to know how much the behavior of the network can differ for different inputs. Right, so once you're here, you rewrite the system up there in a slightly different form. So you put, you flatten your matrices to vectors. So you have to modify a little bit your vector fields, but anyways, it can look like this, where D is essentially, it's quite large, right? It would be, in the example before, it would be 64 squared. So it's already quite large, but anyways, you can deal with this. And what you want to do then is analyze the large scale behavior of this system. So you want to kind of look at the size of the final value of this recurrence, of the solution of this recurrence equation. So this looks very similar to an RDE, if you're familiar with that, just that instead of taking dx here as the driver, you take just the increment of your driving path. Right, so the idea would be to look at Taylor expansions morally.
Sorry, why did the weight go outside of F? The weight was inside F before.
Right, so this is what we propose. You modify your architecture a little bit, and you can put it in this form. So yeah.
But what architecture corresponds to this form?
So you would need to apply an extra nonlinearity at the beginning. So here. And then you see that when you do this, since you're applying nonlinearity x, nonlinearity x, nonlinearity weight, if you apply one extra at the beginning, you can put it in that form. So you absorb all the intermediate layers between the skip connections inside the F, and then you apply one extra at the beginning, and then you do this. You can get it to this form.
So the nonlinearity is not applied to the weighted sum.
Yeah, it's hidden in the F. So somehow you have some intermediate weights that you're using, but you're only looking at the update in the skip connections.
So F depends on WJ?
In the intermediates, not on the ones that skip connections. So somehow the weights that are here.
Yeah, but if you look at your equation on this slide, W is inside the weight.
Yes.
And then in the next slide, it's outside. So
yeah, but I mean, yeah.
So this corresponds to a linear layer where you multiply by the weights.
Yeah.
And then, okay, so
Mm.
are you going to explain the architecture corresponding to this?
Well, let's say that, yeah, for the moment, I only can say that you sort of look for an architecture that has this form.
Okay.
Yeah. Okay, so the idea would be to look at large increments or large differences in time steps. So what you have here is kind of the exact step or the exact form for one step in your evolution. And you would like to know what happens when you look at differences in more than one step, right? And what you can do is you say, okay, it looks like a Taylor expansion where the dots have to be filled in plus some remainder, right? Because this won't be this part here after the YK won't be actually the exact form of this difference here, right? You will need to sum all the intermediate increments. But anyways, you could say that it looks like this terms here plus some remainder that you hopefully can control. And okay, if you think about it a little bit more, then you would see that what you need to put in here is this sort of iterated sum, which again resembles an iterated integral of the path x against itself. So this would be like x dx, left point Riemann sum. Okay, so you're in good shape, you think, because this looks very much like the things you would get when you're doing rough analysis. But you bump into one problem, which is that these monomials here that you have put in front of your vector fields don't satisfy the shuffle relations. So this actually doesn't correspond to a geometric setting. Okay, so what can you do? You actually observe that you have this identity instead. So you take the symmetric part of this matrix. So it's the increment, it's the product of the increments of your original paths, but you get this cross variation term between the direction A and direction B. So this looks like an stochastic bracket, but this in a discrete setting. So to handle this, you are led to introduce new letters if you want. So now I introduced a single letter, which I denote by bracket AB, which I associate with this extra term that I got. And of course, you observe that this is also symmetric in AB. So if I exchange B and A here, since this is just a product of real numbers, I get the same if I look at bracket AB or bracket BA. So inside the brackets, the letters should commute because they are describing the same number. And then once you add these extra symbols, then you actually obtain an identity that looks like this. Where, okay, I have extended this bold x, the definition of bold x, linearly. So if it looks at AB plus BA plus bracket AB, it would be the three terms that appear up here. So now kind of you have restored the character property of your signature map, if you want, which was destroyed by looking at these discrete sums. And it turns out that you can do this for any number of iterated sums that you want. And this has a name, and it's called the quasi-shuffle algebra. And it's defined like this. This was already presented by Patrick Monnier on Monday, I believe. But in essence, you have a shuffle product, which is perturbed by a contraction part, which is here. So if you were to set AB to 0, so this bracket AB would be 0 for any AB that you put, you would recover the shuffle product, which essentially tells you that this cross variation vanishes, which corresponds to the usual Young integration for finite variation paths. So again, you can build a Hopf algebra over these symbols using this product. Here, this delta is the usual deconcatenation. And you also need to change the grading, because now you need to assign weight different from 1 to the single letters here, which kind of tells you that you're looking at higher order variations of your path. So this weight here that you put in your product reflects sort of the p-variation that you're allowing your iterated sums to have. Right. And then you can recursively define the monomials that you would put in front of your vector fields. So as we said before, for a bracket of letters, A1 to AN, you would assign this single sum, which is some sort of correlation between the directions in the components in the vector given by A1 to AN. Again, this value here is symmetric in the letters A1 up to AN. So if I permute the letters here on the left-hand side, I would get the same number. This is why I need to look at the commutative semigroup. So I allow to multiply my letters, but I make them commute. Semigroup just means that I'm looking at only monomials. So I'm not allowed to take sums of this. And then when I have a letter containing these brackets, all I do is I left point integrate. Sorry, these W's should be used here. So I take the previous value that I had and I discretely integrate with the value corresponding to the last letter. And this resembles very much how you would recursively define the signature of a path of finite variation. Right, so you can prove that actually the example that I showed you before generalizes. So you have this type of relation for products, not only of your increments, but also of your cross correlations. You can rewrite them in terms of only iterated sums, strictly iterated sums. And moreover, you also have chance identity, which is very familiar from rough paths and allows you to kind of handle these Taylor expansions. Right. So what theorem do we prove? So one thing we prove is that you can find vector fields which are recursively defined like this. So you know exactly what to fill in the ... that I showed you in the Taylor expansion before. So these are defined according to the letters in your words. So you take the first letter in your word and you split it into the previous vector fields that you already defined, and you take a kth derivative of the vector field corresponding to you here. And then you know that the difference in the increment between two steps of the evolution that are far apart, when you subtract this term here, it's very small. It's controlled by the p-variation of some remainder terms and the p-variation of the iterated sums that you picked. So if you're familiar with rough paths, this is the kind of statement that you would get by an application of the Sui lemma, and this is exactly how you prove it. So if you write it out, what it exactly tells you is that if you look at the increment of your solution to your recurrence equation, then of course at first order looks like the vector field at the left point times the increment of your path. If you go to second order, then you get the composition with the vector of the vector fields with themselves times an iterated sum. Up to the third order, it looks like some vector field, which is again the composition of FA, FB, FC with themselves times third order iterated sum. So all these first three terms are familiar from geometric rough paths, but this fourth term here is new. So you actually get some symmetry factors, which are written here in the statement of the theorem. So this would be 1/2, which corresponds to the symmetry that's introduced by this bracket here between C and B. And you need to take some derivative of your vector fields again that's indicated by the letters here, which is this recursive definition up there. And you can continue in this way, computing all the terms that appear in your Taylor expansion. You can stop at whichever order you want, depending on P. And you can get this sort of estimates. Okay, this is not the whole story because this is not the quantity we aim to control, but we rather wanted to control the difference between two outputs given the inputs. But this is a first step towards proving this kind of results.
Maybe just to tell you that you have a couple of minutes.
Okay, yeah, I have a lot of slides, but I don't plan to show them all. Okay, and so after you have such a bound like this, then a standard argument gives you that you can control the p variation of your solution by a rough path norm of these iterated sums. Of course, here you don't need any assumptions on the driving path, because since these are all discrete discrete sequences, any p variation that you want exists. So it might be very large, but it's finite anyways. So you can play around with the p here. So the point of all of this is to have a chain of estimates for all different p's, and then you can optimize, somehow choose the best p that's suited for the control that you want, given that you know how to compute all these quantities. And finally, you can apply a rough sort of rough-Rungal estimate to obtain a good control, not only on the difference of the output values, but on the difference of the evolution of your features along the network, along the network for any step between skip connections. And it only depends on the p variation of your path, of your weights. Right. So just to show you a few examples, this is again coming back to the first example that I showed you. I took the same evolution of the weights that I showed you in the previous plot, and I plotted here in blue the evolution of one of the features. So you see that it looks not that smooth. And actually, when you do these bounds, this is the size. So here in yellow is the size of the output. And you see that if you stayed kind of in the usual framework without, so looking only at the one variation of your solution, you would get not such a good bound. But as you increase p, you can get better control on the size of the output, right? And you can actually continue for whichever p you want, and you would get different tighter and tighter bounds. Okay, this I believe can be improved. This is part of the work in progress. So if you choose to evolve your network, or if it happens that the weights of your network are smoother, so say you penalize, you can still apply this this framework and get, of course, here the good p, the p that gives you a tighter control. It's lower than the previous one, right? Just because your path is smoother, so it has so it's p variation for lower p, it's already small. And if it happens that your weights turn out to be even rougher, so you can get again the solution here, and right, so you can get different bounds for different p's, and you can try to optimize over p. And the point of the theorem that I showed you before is that you can actually know what this blue curve is for any p you want, and for any range of p you want. So you can try to pinpoint the best p for your given weights. And as promised, this is sort of the control you would get for the difference in two solutions. So here I took the same example as before, and I evolved it from different values of the initial features. So here 1 and 1.2. This is the difference in the final value after you have evolved, so the output. And the p equal 1 bound that you get is very bad. So this is what you would get from the Java and root auto framework. But if you allow yourself to increase P, adding all this framework on top, then you see that you can get a much better control over different ranges of P. Okay.
I think, yeah, okay.
Yeah, thanks for your attention.